This is Rolle's theorem. Suppose that the function f is continuous on a closed interval ab, and suppose that f is differentiable on an open interval ab, and suppose f of a equals f of b, then there is some c such that a is less than c and b is greater than c, where f prime of c, the derivative, equals 0. And we'll give a proof now, and we'll just sketch this to see what I mean. And this should be actually touching the graph as a tangent, a derivative, which should be parallel to the x-axis beneath. Now, since f of a equals f of b, the graph y equals f of x is the same height above the x-axis at the two ends, x equals a and x equals b. So there is some point c between a and b where the tangent is parallel to the x-axis. So there exists some point c such that the derivative of c equals 0. Now, since f is continuous on a closed interval ab, f is bounded on ab. Now, m sub f of x, which is between which x is greater or equal to alpha, and a, and b is greater or equal to x, and m inf of f of x, where x is greater or equal to a and b is greater or equal to x, will let f of a equals f of b equals k. Then m is less than or equal to k, and m is greater or equal to k. Now, if m equals k equals m, then f of x equals k for all x, such that x is bounded between b and a. And hence the derivative with respect to c equals 0 for all c, such that a is less than AC is less than CB. If m does not equal m, then m is less than k, or m is greater than k. Now, suppose that m is greater than k, then there is some point c with c between b and a at point f of c equals m. Moreover, f prime of c exists by condition 2, because our c is bound between b and a. Now, for all x within that closed interval ab, f of x is less than or equal to m, and because c is bounded between b and a, now for all x contained within our closed interval a and b, f of x is less than or equal to m, and hence if x is bound between c and a, then for f of x minus f of c over x minus c equals f of x minus m over x minus c, which is greater or equal to 0 as x goes to c. So this is the derivative here with this derivative of c. Now, therefore, the f prime of c is greater or equal to 0. However, x is bound within b and c. So this is this is less than or equal to 0. And as x goes to plus c, this goes to our derivative of c. Hence, 0 is greater than equal to f prime of c. Since f prime of c satisfies these conditions, we must have f prime of c equals 0. Similarly, k greater than m, it can be proved that f prime of c1 equals 0 at a point c1 at which f c1 equals m. An example: x e to the sine of x equals cosine x has a root on interval 0 to pi over 2. Now, we use Rolle's theorem to prove that it does not have more than 1. We'll write f of x equals the function here, as we're subtracting cosine and putting it on that side. Now, then f is continuous on all parts of the reals and differentiable. If there are two distinct roots, x equals a, x equals b, of equation in the region 0 and pi over 2, then 0 equals f of a equals f of b. And by Rolle's theorem, f prime is 0 at some point between a and b. Moreover, f prime of x equals e to the sine x plus x cosine x, e to the sine x plus sine x. And for our x between pi over 2 and 0, f prime of x is greater than e to the 0 equals 1, since f prime does not have a 0 on pi and between pi and 0 and pi over 2. The equation cannot have more than one root on 0 pi 2. Thus the equation has precisely one root between 0 and pi over 2. And that's Rolle's theorem.